So we've just figured out how to color a rational tangle using integers. So we have a whole infinite crayon box that we can choose from, and we've figured out a scheme to associate with every arc in a rational tangle diagram an integer in a way that gives us a valid coloration. And we figured out how that tells us something about the knots and the links that are associated with that rational tangle. What we haven't yet figured out is what that tells us about the tangle itself, and this is the super exciting part. In this video, we're going to figure out what are the relationships between integer colorations of a rational tangle and the complete invariant for rational tangles that we know, the tangle number, or the fraction. So in our previous video, we used the integer coloration scheme to color this rational tangle, and we figured out that when I chose 0 for this strand here in the northwest and 1 for its overcrossing strand, and then applied that rule to color the rest of the tangle, then the color matrix that we got out of this process looked like 1, -22, 15, -8. And we made a couple of observations at the time. We observed that it didn't matter whether I subtracted the integers across the top or across the bottom, I got the same difference. I got 23 when I subtracted the tops, and I got 23 when I subtracted the bottoms. Likewise, the right difference ended up being the same as the left difference. Those both are separated by 14. So we observed that if I call my color matrix A, B, C, D, that the difference B minus A was the same as the difference D minus C, both of those are 23, and that the difference C minus A was the same as the difference D minus B, both of those were 14. So what does that mean? Another way to say that, if we rearrange each of these equations, is that each of those is equivalent with the so-called diagonal sum rule. The diagonal sum rule is the statement that the sum of the diagonal of this color matrix, the trace of the color matrix if you like, is equal to the sum on the antidiagonal, the antitrace of the color matrix. And so we can see that just by adding them both up, finding out they're both equal to -7. So we tend to think of it as a diagonal sum rule rather than as a difference rule. I think mainly because addition is commutative. That way we don't have to remember which comes first, right? The diagonal sum rule says that A plus D is the same as B plus C for the color matrix of any rational tangle. So let's prove it. Since we're dealing with rational tangles in particular, we know exactly how to define rational tangles inductively. A long time ago, we talked about rational tangles as being inductively defined by taking an empty tangle and applying a series of combinations of twists and rotations to that tangle. So we can use that definition to come up with a proof by induction. This proof is going to have 4 base cases. The 2 empty tangles, the horizontal one and the vertical one, and then the 2 single twists, the positive twist and the negative twist. So let's verify the diagonal sum rule holds for each of these 4 base cases. For the horizontal, the only way really for me to color it is to give the strand up top the color X, the strand on bottom color Y. For the vertical tangle, give the strand on the left a color X and the strand on the right a color Y. Is the diagonal sum rule satisfied in each of those cases? It absolutely is, because in both cases the sums are just X plus Y, so those are trivial. The case where we actually have a crossing is a little bit more interesting, but not a ton. If I color the overstrand here X, and I color the understrand Y, then according to our scheme, the color of this remaining strand should be twice the over minus the under. In other words, 2x minus y. Is the diagonal sum rule satisfied for this simple tangle? Sure. I just add up the diagonals, I get 2x, and on the other hand, 2x minus y plus y. So 2x. Same process applied to our last base case. If I choose x to be this understrand and y to be my overstrand, and then I use our scheme to compute the color of the third strand here, 2y minus x, twice the over minus the under, then the diagonal sums in this case are equal because they're both 2y. So my base cases are all satisfied. Now I just have to satisfy the inductive step. So I make my induction hypothesis. My induction hypothesis is that if I start with a rational tangle G that has n crossings in it, I'm going to assume that the diagonal sum rule is satisfied for that tangle. My induction step is going to be then to figure out whether the diagonal sum rule is still satisfied for that tangle having been operated on by a twist, and that tangle having been operated on by a rotation. So TG and RG. Do TG and RG satisfy the diagonal sum rule, given that G satisfies the diagonal sum rule? So we'll go one at a time. First, let's look at TG. This is this tangle G with an extra twist over the top right over the bottom right, tacked onto the right side. So how must we color these strands? Well, this overstrand here is connected to the C up top, so its color has to still be C. But the strand which ends up in the northeast corner of this tangle, we figure out its color using our coloration scheme, twice the over minus the under, 2C minus D. Is the diagonal sum rule satisfied for this new tangle? Well, on the one hand, one of the diagonals adds up to A plus C. On the other hand, the other diagonal adds up to B plus 2C minus D, and it's not immediately obvious that those two are equal. So how can we figure out if they're equal? Well, we can take and add and subtract D from the one on the bottom. So A plus D minus D plus C. So we introduce D into this equation because we have a D up here we'd like to somehow connect with. But now is a place where we can apply our induction hypothesis, which is how we know this is really an inductive proof. According to our inductive hypothesis, A plus D is equal to B plus C. So I can replace the A plus D in this expression with B plus C instead. And once I do that, I get B plus C minus D plus C, which is indeed B plus 2C minus D. So we verified that the fact that the diagonal sum rule was satisfied for G implies that the diagonal sum rule is satisfied for TG as well. That's one of our two inductive steps. The other step is we need to verify that this also holds for the rotation. That given that the diagonal sum rule is satisfied for G, is it also then satisfied for RG? This one's much faster. After I've rotated my tangle, my new diagonal sums are C plus B and D plus A. But those are already the same things as A plus D and B plus C, which according to the induction hypothesis were already equal to begin with. So that proves that every rational tangle will satisfy this diagonal sum rule, according to this induction proof. So now we know anyone hands me a rational tangle, and any way that I color that rational tangle, any way that I choose to color it, will satisfy this diagonal sum rule. That seems super important. What else? What other mileage can we get out of these rational tangles? We can also ask what happens to the coloration when I add a twist to a rational tangle. We saw kind of an example on the previous slide. So what's going to happen if I apply a new twist to a rational tangle? So let's take the tangle we've been working with here. Its diagonal sum was -7. The top difference, and when I say top difference, what I'm going to mean is this entry minus that entry. So that ends up being -23, which is the same on the bottom as it is on the top, according to the diagonal sum rule. And its rightward difference, which I'm going to think of as this number minus that number, that right difference is -14. So that's what we know about this original tangle. Now what's going to happen if I tack on one more twist? If I apply T, which is going to rotate the top right over the bottom right and give me a new twist over here on the right side. What's the new diagonal sum? What's the new top difference? And what's the new right difference? Well, over here on the bottom right I have -22, the same color as the old northeast corner. And my new northeast corner I have to apply my coloration scheme. It's twice the over minus the under, twice -22 minus -8. That's -36. So my new diagonal sum is -21. That's 1 plus -22. My new top difference is -37, -36 minus 1. And my new right difference is -22 minus -36. It's actually the same as my old right difference. So when I add in a twist into a rational tangle, the right difference, this vertical difference here, that remains the same. But the difference on the tops changes. And it changes exactly by an addition by the right difference. So it takes the right difference and it adds it into the top difference. You'll also notice that it adds it into the diagonal sum as well. Okay. So when I apply a twist to a rational tangle, the right difference gets added to the top difference, but the right difference remains the same. And you'll notice that that's true in general, not just for the tangle that we just looked at. So if I have a tangle that has color matrix A, B, C, D, and I add in a twist to it, now the southeast is going to be B, the northeast is going to be 2B minus D, twice the over minus the under, that's our coloration scheme. And so my new top difference is going to be this minus this, 2B minus D minus A. But that's the same thing as B minus A plus B minus D, right? It's the same as the right difference added into the top difference. So that's what always happens anytime I add one twist into a rational tangle. The right difference gets added to the top difference, but the right difference itself remains the same. Okay, how about the other operation on rational tangles, the rotation? What's going to happen to this data when I apply a rotation to my rational tangle, counterclockwise rotation of 90 degrees? So looking back at our original tangle, same diagonal sum, top difference and right difference as before, if I rotate that tangle 90 degrees counterclockwise, I get this new tangle. So what is this tangle's diagonal sum? Well, this tangle's diagonal sum is still the same as the old diagonal sum was. Negative 22 plus 15, still negative 7, so that's fine. But pretty clearly, what this rotation is going to do is it's somehow going to reverse the roles of the top difference, the difference in the purples, and the right difference, the difference in the greens. Let's look at exactly how that works. The diagonal sum remains the same, but my top difference, which we defined as the northeast minus the northwest, now that top difference used to be negative 23, now it's going to be not even 14, but not even negative 14, but positive 14. So this top difference is the old right difference, but the sign has changed. Right? You notice the direction that my arrows are oriented here. I had to reverse the direction of this arrow here. So my new top difference is the opposite of my old right difference. Meanwhile, what's my new right difference? My new vertical difference? Well, those arrows are still pointing in the right direction to give me this. It's really just this entry minus that entry, negative 8 minus 15, which is the same as my old top difference on the nose. So when I applied a rotation to this rational tangle, my new top difference is the opposite of my old right difference, and my new right difference is the same as my old top difference. So something interesting is happening here. If we take a look at what's happening to the combination of the top and right differences under these two transformations that fundamentally define rational tangles, the top difference, when I add in a twist, is changing to the top plus the right, and the right is remaining the same. Meanwhile, when I rotate, the top is turning into the opposite of the right, and the right is turning into the top. And this arithmetic looks kind of familiar. It kind of looks a lot like the kind of operations that we did when we were working with fractions. So what fraction operations are we really doing here? If I put a fraction bar in between the top and right differences, then this operation up here on top, where the top changes to the top plus the right changes to the right, that's the same as the numerator having the denominator added into it, while the denominator remains the same. Meanwhile, the operation of rotation seems to have traded places of the numerator and denominator and also tacked on an opposite sign. What is this in fraction arithmetic other than, respectively, the operation of adding 1 to a fraction and the operation of taking the opposite reciprocal of a fraction? These are operations that we have seen happening to the tangle numbers of rational tangles already, quite a long time ago. And so this gives us a really powerful clue that this set of data that we've computed by the coloration of a rational tangle must have something fundamental to do with the tangle number for that rational tangle. And it turns out that that answer is absolutely yes. That if we define that fraction, this is the top difference divided by the right difference, defined by the color matrix of the coloring of a rational tangle, then we would like for that to have a very intimate connection with the tangle number. All we have to do first, before that's going to be true, is we need to check that this fraction is independent of the colors that we chose in the beginning, the 0 and the 1 that I used at the northwest corner to get my rational tangle coloration started. So let's just check to make sure that this fraction is independent of how we started off that coloration. The way we're going to do it is by taking an arbitrary tangle with color matrix ABCD and look at one of its crossings here in the middle. So I'll use beta for the overstrand and alpha and gamma for the understrands, where gamma satisfies 2 beta minus alpha, so it's according to our coloring scheme. So we have a validly colored rational tangle here with matrix ABCD. What's going to happen if I take all of the integers in that coloration and multiply them all by a constant n? So a turns into na, b turns into nb, n alpha and n beta. So what's going to be the color of this green strand here? According to our scheme, it's twice the over minus the under, so twice n beta minus n alpha. But on the other hand, that's equal to the same as if I factor the n out, n times 2 beta minus alpha, or n times gamma. And what this shows is that if I start with a valid coloration of my rational tangle, and I multiply all of its colors by the same n, I'm going to get another valid coloration of the same rational tangle. So in other words, the validity of colorability doesn't depend on whether I multiply everything, scale it all up by a constant n. Okay, well that handles multiplication. What happens if instead I decide to add something to all of my colors? So take a valid coloration and add the same k to every color. Do I still get a valid coloration? So I replace my color matrix with A plus K, B plus K, C plus K, D plus K. This color here, alpha plus K. This one, beta plus K. Do I still have a valid coloration? Well, let's use our scheme to figure out what the color of this under arc right here has to be at this crossing. It's twice the over minus the under. But if I do the algebra out, that's the same as twice beta minus alpha plus twice K minus K. And twice K minus K equals K. And therefore that's gamma plus K. In other words, if I take a valid coloration and I add the same K to every single color, I get a new valid coloration. And so the upshot of all of this is that it doesn't matter which colors I started my coloration with in the beginning. I chose 0 and 1, but we could have chosen any two integers to start off my coloration. I will get a valid coloration through this process, and therefore this fraction that we get out of the color matrix is going to be an invariant of my rational tangle. And since on the previous slide we also showed that it obeys all the same properties that the tangle number does, in fact, this ratio of top difference divided by right difference is not only related to the tangle number of that fraction, it is exactly the tangle number of that rational tangle. So what we've won in this process is we've discovered a brand new way to compute the fraction, the tangle number, of a rational tangle. All we have to do is apply our coloring scheme to that rational tangle, obtain its color matrix, and then just divide the top difference by the right difference of that color matrix, and we're done. That gives us the fraction, the tangle number of that rational tangle. This is so cool that I feel like we need to verify it. So let's finish this video by doing one example of using this coloring scheme to compute the tangle number for a rational tangle. We'll return to this same tangle that we've been working with over the course of the last two videos and see how it works. So here again, I chose 0 and 1 at the northwest corner to get my coloration started. I applied the twice over minus under scheme to give me all the colors of the rest of the strands. And at the end, I end up with this color matrix, 1, negative 22, 15, negative 8. The color fraction for this rational tangle is defined as the top difference minus the right difference. Negative 22 minus 1, that's going to give me negative 23, divided by negative 22 minus negative 8, that gives me negative 14. And so the color fraction for this rational tangle is 23 over 14. Is that the same as the tangle number that we would have gotten for this rational tangle using our older methods for computing tangle numbers, which the old method was the continued fraction representation method? So for that, we have to interpret this rational tangle as a continued fraction rational tangle. To do that, this one happens to already be in a friendly canonical form for us to make that happen. In particular, we've got 2 twists over here, followed by negative 3 twists over there, followed by 5 twists over there. So the continued fraction representation for this is 2, negative 3, 5. And we can check that that as a continued fraction in the rational numbers is 2 plus 1 over negative 3 plus 1 over 5. Do the arithmetic out. It turns out to be 23 over 14. Anytime you see accidents like that happen in mathematics, they tend not to be accidents. And the results of this video just showed that by applying our integer coloration scheme to rational tangles, we can get a new invariant for rational tangles that turns out to be the same as our old invariant for rational tangles. And so using the integer coloration scheme on a rational tangle computes for us the tangle number of that rational tangle. And I think that's pretty cool. You can see all the details worked out for this in Kaufman and Lambropoulos' paper about a classification of invariants for rational tangles.